Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 13 from the course, but make sure you have watched the previous ones before viewing this one. In the last lecture, we discussed about the postulates of the BOHR'S atomic model, and I hope they are clear with you. Till the last lecture, we've learned a lot of theory related to the structure of atom, and now it's time to put all the learned information into some mathematical expressions, and this is the topic for our today's lecture. We would be discussing the mathematical expression for the BOHR'S atomic model, wherein we would be discussing about the velocity of electron and the radius of the BOHR'S orbit. And this, I think, is going to be a very interesting lecture for you. And also, it forms a very important topic as far as your exams are concerned. Many questions, be it subjective or objective exams, are framed from this topic. So please be very attentive while you understand this lecture. Now, what do we mean by the term mathematical expression of BOHR'S atomic model? If you remember in the last lecture while we were discussing the BOHR'S postulates, he said that the electrons, they are moving in the fixed paths called as orbits. So the distance of these orbits from the nucleus, that is fixed. Then he said the energy of the electrons, that is fixed. The velocity with which the electrons are moving, that is constant, so that is also fixed. The momentum, that is also fixed. So many things just fixed, that is what he was saying all about. So if the velocity, the radius, the energy, they all are fixed, they must be having some definite value, and that is what we are going to find out in this lecture in the mathematical expression form of the velocity, the radius in this lecture, and continue the lecture in the next and discuss about the energy. Now, the BOHR'S atomic model, this explains quantitatively the general features of the structure of hydrogen atom and its spectrum. But this is also valid for hydrogen-like species. That means the isoelectronic species of hydrogen, those have one electron each. For example, we have He plus, lithium plus 2, beryllium plus 3. They all have one electron. So they are hydrogen-like species, and all the expressions that we derive for hydrogen, they would be valid for all these, right? The only difference would be in the atomic number Z for them. Now, if you remember, while discussing the Rutherford's model also, he said that the electrons, they are moving around the nucleus and they do not fall into the nucleus because the electron, that is being pulled inwards due to an electrostatic force of attraction, and that inward pull is balanced by an outward pull, that is the centrifugal force, due to the circular motion of the electrons. So here also the electron, this is stable in its orbit because of these two forces. The electrostatic force of attraction Fe between the revolving electrons and the nucleus, this provides the requisite centripetal force to keep them in their orbits, such that Fe is equal to kZe square by r square. So the electrostatic force of attraction that is given by Coulomb is equal to K into Q1 into Q2 by r square, where Q1 and Q2, they are the charges. So if they are the charges, what are the charges we have in the atom? We have a positively charged nucleus, and what will be the value of that charge? Z is the number of protons multiplied by the charge on proton, and because in magnitude it is equal to the charge on electron, so we are writing that charge to be Ze, and on the electron the charge is going to be E. So the total charges Q1 and Q2, they become Ze square. And what is K over here? K is the Coulomb's constant, and the value of this is going to be 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free air, and this you would be able to understand when you study this in physics. For me, the value, the K is equal to 1 over 4 pi epsilon naught, and the numeric value for this comes up to 9 into 10 power 9 joule meter per Coulomb square. Right? And please do remember this also, because you are going to need it in your further calculations. Okay, now we have the electrostatic force, and what is the centrifugal force? The centrifugal force is mv squared by r, again coming from physics. For a dynamically stable orbit in a hydrogen atom, we have the electrostatic force balancing the centrifugal force. So both are equal. Hence we can write that mv square by r is equal to kze square by r square. And now this is going to be a very, very, very important relation for you, because this is going to help you derive the formulas for all the radius of the orbit, the energy, potential energy, kinetic energy, the velocity of an electron in an orbit, right? So this formula, how it has come and what the formula is, what is this equation basically. So you should remember this. This is going to be really helpful to you. Now the first expression we are going to derive is the velocity of electron revolving in an orbit of radius r. And now you know this equation also, mvr is equal to nh over 2 pi. What is this? This is the angular momentum which Bohr said is conserved in an orbit while the electron is moving. So mvr is equal to nh over 2 pi. This equation and the Rutherford's equation, both of these, they are utilized in the derivation of all the velocity, radius, energy, etc. So let us see how we derive first of all the velocity. From the first equation, that is the Rutherford's equation, what do we have was that mv square by r is equal to kze square by r square. So r and r, one can cancel. The remaining r we can take to the other side. It would become mv square r is equal to kze square. And we can write that mv square r as mvr into v. And now we know that mvr is nh over 2 pi. So we can substitute the value of mvr by nh over 2 pi. So what we would get from these equations is that kze square is equal to nh over 2 pi into v. Or we can say that the v, the velocity of the electron, is 2 pi kze square over nh. Right? So this is the expression for the velocity of an electron in an orbit of radius r. Right? So now if you see, first of all, you should know how we have got this. And next, the thing which we can see over here is that 1 is Z, the atomic number that is going to change for every element. And then we have N, that changes according to the number of the orbit in which the electron is. Rest 2 pi k e square h, they all are constants. So 2 is a constant, pi is 3.14, k we have just now said that it is 9 into 10 power 9. Then we have E, the mass of charge on electron, that is 1.6 into 10 power minus 19, and H, the Planck's constant, 6.626 into 10 power minus 34. So all these values, they are constant. So we can just calculate what becomes the value of all these. The value of all this becomes 2.18 into 10 power 6 meter per second. So this you do not need to calculate every time when you are solving your numericals. If you know this, you just have to simply put this and multiply that by z and divide it by n, you will get the velocity of the electron, right? So we have the velocity of the electron to be 2.18 into 10 power 6 into z by n meter per second. And now this also means that the velocity of the electron, that is directly proportional to z. So as the atomic number is increasing, the velocity of the electron is increasing, and it is inversely proportional to n. So as the number of the orbit is increasing, the velocity is decreasing. So farther we are going away from the nucleus, the velocity of the electron is decreasing, right? So the next expression we have to get is of that of a radius of an orbit. And we already have the equation that kze square is equal to mv square r. So we can say that r is kze square over mv square. Now simply what we have to do is that the velocity value that we derived in the last slide that we saw, just put that over here instead of v. Okay, and what will you get the velocity of r to be? N square h square over zkm 4 pi square e square. So this becomes the expression for radius. So how we have calculated radius? Again we can say that we have utilized the Rutherford's equation as well as the Bohr's equation of the angular momentum, and we can even get the radius. Fine. Now if you see again at this equation, what do you get? N square and z, these are the variable terms, the rest are constants. So calculate the value of those constants. Here the constant we have added is the mass of electron, that is 9.1 into 10 power minus 31 kg. So you can put all them, try to calculate them, you will find that the value comes up to 0.529 into 10 power minus 10 meter, and this we have denoted by the symbol A naught. And this A naught, this is called as the Bohr's radius. Okay, so now our n, that is of the nth orbit, the radius, that can be written as A naught into n square by z, where A naught is 0.529 into 10 power minus 10 meter into n square and divided by z. Fine. So normally the electron of the hydrogen atoms, the Z is 1 and it is present in the first stationary orbit. So N would be 1. So what would be the radius of the first stationary orbit of hydrogen? That R1 is 0.529 Armstrong, right? So, and this would be equal to 52.9 picometer, where 1 picometer is 10 power minus 12 meter. So this basically 0.529 Armstrong, this is the Bohr's radius. So if in a question you are said that the Bohr's radius is this much, so you are given the Bohr's radius, something of that sort, whatever is the question. So Bohr's radius would mean that the electron is present in the first orbit of hydrogen and the value of that radius is 0.529 Armstrong. Also from this slide, you can understand one more thing, that the radius is directly proportional to n square and inversely proportional to z. So this is also very important. Why that radius proportional to n square is important is because that makes us understand that different energy levels are not equally spaced. So the radial distance between two successive energy levels does not remain the same as we move away from the nucleus, and the difference goes on increasing with increase in the value of n, because r is directly proportional to n square. Now this means what? Say we have r equal to n square. If n would be 1, r would be 1. If n is 2, r becomes 4. And if n is 3, r becomes 9. Right? So first of all, one thing would be that with the increasing value of n, the value of r is increasing. And then the difference between R1, R2 and R3, they are not the same, and with the increase in the number of n, that difference is increasing. Between 1 and 4, the difference is 3, and between 9 and 4, the difference is 5. right? Similarly, over here also, the radial distance between two successive energy levels will not remain the same. The difference is increasing because R is proportional to n square. And you can see the radius of the various energy levels. We have the formula Rn is equal to n square A naught, and A naught, the value is 5.29 into 10 power minus 11 meter. This being written in the SI notation. Right? So when we put the value of n to be 1, what do you get the value of Rn as? 5.29 into 10 power minus 11 meter. When it is n equal to 2, what would be the value of R2? If you calculate, this would come up to 2.116 into 10 power minus 10 meter. Then R3 comes up to 4.76 into 10 power minus 10 meter. So the difference between R1 and R2, this is less than the difference between the R3 and R2. Okay, so that is what we are trying to say over here, that the different energy levels, they are not equally spaced, and the difference is increasing when we are increasing the value of n. And N4 also, you can see the value of R 8.46 into 10 power minus 10 meter, and R5 1.32 into 10 power minus 9 meter. Again, all signifying the same thing, that the different energy levels not equally spaced. So let us see a question on the radius. So we have to calculate the ratio of second orbit of helium plus 2 ion and the third orbit of beryllium plus 3 ion. And the Bohr's radius is given by the formula Rn is equal to 0.529 into n square by z Armstrong. So R2, the radius of the second orbit of helium plus 2 ion, would be 0.529, n being 2, so we have 2 square, and z also for helium is 2. So this is going to be 2 square by 2. And the radius of the third orbit of beryllium plus 3 ion, this is going to be 0.529 into 3 square because n is 3 divided by 4 because the z for beryllium is going to be 4. Right? So now we have to take the ratio of R2 by R3. So this we are going to solve and get as 8 by 9. Now the next question says that if the radius of the second orbit of lithium plus 2 ion is x, then find the radius of the first orbit of helium plus in the terms of x. So we have the radius of the second orbit of lithium plus 2, say it is R1, and that is going to be equal to 0.529 into 2 square because n is 2, and then z for lithium is going to be 3, so divided by 3, and this is given to us to be x. And then R2, the radius of the first orbit of helium plus ion, this is going to be 0.529 into 1 square by 2, right? And now what we are going to do is, we are going to substitute the value of 0.529 in terms of x. So this we will get as x into 3 and divided by 4. So this is going to be 0.529. So we get 0.529 to be 3x by 4 multiplied by 1 by 2. So the radius in terms of x becomes 3x by 8. So that would be all for this lecture. I hope that all that we discussed today about the velocity, the radius, they are very clear to you, because this is a very important topic as far as this course is concerned. Many questions coming from this. So please, if you have still any doubts, you can mail us at h2ochemistry@gmail.com also. Put that in the comment section also. We'll be glad to help you all. In the next lecture, we would be continuing our discussion further about these mathematical expressions, and we would be discussing about the energy of electrons in the Bohr's orbit. And now if you've liked the lecture, please do click on the like link. That motivates us a lot to work more for you. And also do subscribe to our channel H2O and click on the bell icon so that you get a notification as and when we put up a new course for you, a new lecture for you. Have a nice day. Enjoy yourself. Meet again for lecture 14.